In today's lecture, we are going to talk about something related to maximum minimum. It's called the method of Lagrange multipliers. So what are the kind of problems we are going to deal with in this is as follows. Let us look at the following function defined on R3 given by f of x, y, z. This is a very simple function, x square plus y square plus z square. Now suppose I ask you that what is minimum of f suppose I ask this question, then obviously the answer is 0 because x square plus y square plus z square is always bigger than or equal to 0. The minimum possible value then is 0 and the minimum is achieved at 0, 0, 0. So that is very simple. But suppose I ask you that what is minimum of f x y z such that 2x plus 3y plus 4z equal to 1. See, now the question is very different because the global minimum of the function is at the point 0, 0, 0. But that point does not satisfy the given equation 2x plus 3y plus 4z equals to 1. Okay? So the method of Lagrange multipliers essentially deals with this kind of problems. That is, you want to find extremum of a function subject to the condition that x, y, z is on some surface. In this case, my surface is a plane. So geometrically speaking, what I am asking is that this is same as asking that what is the point on the plane 2x plus 3y plus 4z equal to 1, which is closest to the origin. Usually what you would do is take any point x, y, z on the plane 2x plus 3y plus 4z equal to 1, then see what is the Euclidean distance of that point with the origin, which is square root of x square plus y square plus z square. It is enough to minimize the square of this function, that is x square plus y square plus z square, and you want to find the minimum value of x, y, z such that this function is minimum. So this is a typical example of a constrained extremum problem. Let us look at another example. Let us say, what is the maximum value of the function f of x, y, z, let us say equal to x, y, z. Okay? Now, a moment's thought would tell you that this maximum of the function must be infinity, because it is certainly an unbounded function, because once I fix a value of y and z, x I can choose as large as I like. So you cannot certainly find out a real number which is the maximum value of this function. But at the same time I can add a constraint on it, that is, what is the maximum value of this function such that x square plus y square plus z square equals to 1. That is, what I am saying is now that look at the sphere in 3 dimension. Now a function f is defined on this given by if x, y, z is a point on the sphere, then it is going to x, y, z. I am asking what is the maximum of this function. Now, in all these questions there is something very involved here. in 3 dimension, what exactly we mean by, let us say, maximum, or a local maximum, as we say, x naught, y naught, z naught. This point is a local maximum. What does this mean? That means around this point, so if I draw the picture in 3 dimension, let us say that these are the 3 axes, x, y, z. Suppose this is my point x naught, y naught, z naught. This is the point x naught, y naught, z naught. Then this point is a local maximum means what? It means there exists a ball which looks like this around the point x naught, y naught, z naught, such that for all points in that ball, f of x, y, z is strictly less than or equal to, let us say, f of x naught, y naught, z naught. If I call this ball B, for all x, y, z in B. Okay, this is what is the meaning of local maximum. That a point is a local maximum means there exists a ball around that point such that for each point in that ball, the value of the function is less than or equal to the value of the point where I am saying the function has the local maximum. Now, if I look at the constraint situation, that suppose I am on this big sphere, then what do I mean by f has maximum at this point? That means there exists some portion of the sphere which is given by the dotted line where the value of the function is less than this point. Now notice that this has nothing to do with the usual 3-dimensional ball. For example, if the function has a local maximum at this point, let us say, then among all the neighboring points, the value of the function at this point is bigger than the other points. So this point will then suffice as a local maximum on the sphere, no problem about that. But it might happen that the function has a minimum here, and this point which I am looking at, it is not at all a minimum of the function. But when I am looking at the constraint situation, in that situation, the value of the function at this point is less than the value of the function at the neighboring points. Okay, I can very well see a 2-dimensional situation that look at this line. Okay, look at this point. Suppose the value of the function at all the other points is smaller than this point. So if I call this point x naught, y naught, then if I call this line L, then f of xy, let us say, is less or equal to f of x naught, y naught. This can happen, but whenever I look at any point very close to this, that means if I look at a disk around that point, then whatever disk I choose, there exists a point here inside the disk. There exists a point here inside the disk such that f of x prime, y prime, if I call this point x prime, y prime, here it is bigger than f of x naught, y naught. This is precisely what happens in 3 dimension. It can happen in the case of constrained maximum or minimum. So the upshot of the whole discussion is that our usual method of finding maximum minimum is not going to work in the case of constrained maximum minimum. That means I am searching for extremum or extremum of a function where the points where the function is, the points where I am concentrating on, they are actually varying on some surface. So a typical statement of a constrained extremum problem is something like find maximum or minimum of f such that x, y, z satisfies g x, y, z. equal to some constant. So a typical example which I have mentioned, that find minimum of f xyz equal to x square plus y square plus z square, such that 2x plus 3y plus 4z equal to 1. So in this case, gxyz is given by 2x plus 3y plus 4z. So gxyz equals to 1 gives me the surface which is a plane, and I want to minimize the function on these planes, on this plane. Okay, fine. So the question is, how does one go about it? We have to develop a total new method. Now the point is first to get hold of what is the collection of points where the extremum can lie, and that is actually what is suggested by the method of Lagrange multipliers. And once you get those collection of points, among those points now you have to search, examining the function to see whether you can locate the maximum or the minimum. So let me now describe the method. So I assume f is differentiable, g is also differentiable. I define a surface S which is x, y, z, such that g x, y, z equal to C. I will also assume that grad f not equal to 0 on S and grad g not equal to 0 on S, where we have the obvious meaning of grad f, that is the partial derivatives fx, fy, fz. So that means typically I am dealing with real valued functions here, f and g. Now first I have to get hold of the extreme points. So let us say p equal to x naught, y naught, z naught. Let us say this is a point on S, such that f has local max. Let me work with local max only. Similarly, you can work with local minimum at P. Okay, fine. Now the first thing about S, what I know is that grad g, if I look at any point on the surface, this is the normal. Normal to the surface. Now suppose P is a local maximum at P. Look at the situation here. I will just draw some surface for you. It looks something like this, let us say, and I have a point P here. Okay, I look at any curve passing through P. Okay, then let us say RT is the curve. So the curve RT looks like XT, YT, ZT. This is a curve, and since this curve is on the surface, I also know that g of xt, yt, zt is a constant c. Now look at the function f compose R. By that I mean f of RT. Look at this function. I know at the point P, f has a local maximum at P. That means if I look at, this is my point P, if I look at the neighboring points on the curve, the value of the function at P is always bigger than the value of the function at the neighboring points, because P is a local maximum. So this then implies that if P is given by RT naught, then f compose R has local max at t naught, and then this function is a function on real line going to real line. Our usual one variable results of calculus works, which implies then that d of f compose R dt at t equal to t naught is 0. But to calculate this derivative, I can use chain rule. So this implies grad f dot dr dt at t equal to t naught. Sorry, it's t equal to t naught here, is equal to 0. This then implies that grad f at r t naught dot dr dt at t equal to t naught is 0. Now notice this is happening for all possible curves because it has a local maximum. That is, if I go back to the picture, instead of this I could have taken this curve, I could have taken this curve. All possible curves passing through P if I take, then this relation is true. But dr dt at t equal to t naught, that gives us the tangent plane. So grad f at r t naught is a vector whose dot product with any tangent vector is 0. That means grad f at r t naught is perpendicular to the tangent plane. But this then implies, since the normal is already perpendicular to the tangent plane, that means grad f at r t naught must be a scalar multiple of the normal vector. So this gives me one idea of how to get the extremum points. That is, what I do is I look at the equation grad f equal to lambda grad g. That means I find x, y, z such that grad f equal to lambda grad g, that is number 1. Of course, lambda is not equal to 0. And number 2, g of x, y, z equal to c. That means I am looking at points on the surface. Then, if x, y, z is a local extrema, that is, if it's a local max, then x, y, z must satisfy one and 2. So this actually gives me the collection of extremums, that is the collection of critical points. Among them I have to find the local maximum or minimum, but that will depend on the nature of the function. So let us see the method once again. What it says is that if I want to find the local extremum of a function f on a surface S, which is given by a function g, all I do is first I calculate grad f, then I calculate grad g. I look at the equation grad f equal to lambda grad g. I don't know what is this lambda. I have to find out x, y, z which satisfies this, and x, y, z is a point on the surface. I get a collection of points. There might be too many, I don't know. That is the collection of critical points. Among those points, I will try to find what is the maximum or minimum of the function. So all these things will be very much clear if I look at the following example. Let us look at the following function. Okay, let us look at the following problem. Find a point on the plane (2x plus 3y minus z) equal to 5, which is nearest to the origin. So which function I want to minimize here? Well, the function is obviously the distance function. I look at the square of the Euclidean distance, that is x square plus y square plus z square. This is the function. I want to find the minimum of this on 2x plus 3y minus z equal to 5. So what is my function g here? So g x y z is 2x plus 3y minus z. So let me try to calculate then. What is grad f? Grad f is 2x, 2y, 2z. Okay. Now I have to calculate what is grad g. Grad g can be easily computed. It is 2, 3, minus 1. So what does it mean to say grad f equal to lambda grad g? If I look at this equation, that means 2x, 2y, 2z, that is lambda times grad g, that is 2 lambda, 3 lambda, minus lambda. That means 2x equal to 2 lambda, 2y equal to 3 lambda, and 2z equal to minus lambda. Now I have another equation that is given by g. So the equation is 2x plus 3y minus z equal to 5. So that means 2 lambda, because 2x is 2 lambda, 2y means what? So it is plus, y is 3 lambda by 2, so 3 into 3 lambda by 2 minus lambda by 2, that is my z, that is equal to 5. So this implies 2 lambda, 9 lambda by 2 plus lambda by 2, that is equal to 5. So this implies I have 2 here, 14 lambda here in the top, that is equal to 5. So this implies lambda equal to 5 by 7, which is a simple calculation. Now once I know lambda equal to 5 by 7, then I certainly know what are the points. So let us calculate the points here. That means x equal to 5 by 7, because x equal to lambda, y equal to 3 by 2 into 5 by 7, that means 15 by 14, z equals to minus lambda by 2, but lambda is 5 by 7, that means 5 by 14. That means what? So I found a point precisely 5 by 7, 15 by 14 and minus 5 by 14. Now I always know that there is certainly a point on the plane which is closest to the origin. That means the function which I am looking at, it does have a minimum. That is known from elementary geometry. But here I see that I got a point which is candidate for local extremum, and that is the only point. There is no other point coming. That certainly means that the minimum is achieved at this point only. See what I'm using something here which is not included in the method, because method just gives me the candidates for critical points. I know that there exists a minimum, and luckily I got only one critical point. That means this must be the minimum. So this is the extra thing which is not in the method. So what does method give me? Method give me the critical points. But which one of the critical points is the candidate, that has to be found out by some other considerations, which I am doing it here from geometry. Because I know there exists a point on the plane which is closest to the origin. Given any plane, you can always find a point on the plane which is closest to the origin. So you know it exists. But because of this method, I could exactly find it out, that what exactly is the point. Now let us look at another example. Given positive numbers, A1, A2, let us say up to AN, find the minimum value of A1x1 plus A2x2 ANxn such that okay. Now what does it say? It says that the unit sphere is given to me. The given equation x1 square plus x2 square plus xn square equals to 1 gives me the unit sphere. The given problem is to minimize the function a1x1 plus a2x2 plus anxn on the sphere. What is the guarantee that some such minimum exists? Well, that is given from advanced mathematics. That if I have any closed and bounded region and I have a function which is continuous on that, then the function has a maximum and a minimum. Now the function f of x1, x2, xn equal to, so if I look at the function f of x1 up to xn equal to a1 x1 plus anxn, the function is certainly continuous function. In fact, it's differentiable. So it will have a maximum and a minimum on the unit sphere because it is closed and bounded. So in this case, I want to apply the method of Lagrange multipliers again, because it's a constrained extrema problem. That the given function f is the function, of course, which I want to minimize, and the function g is given by is x1 square up to xn square. Okay. Well, I described the method of Lagrange multipliers only for 3 dimension, but it works equally well if I am looking at higher dimension. So if you want to convince yourself with that, you can assume n equals to 3, no problem with that. But it works more generally. Now fine, I again start with grad f. Grad f in this case turns out to be a1, a2 up to an, and grad g, that is twice x1 twice x2 up to twice xn. So grad f equal to lambda grad g. If I want to solve, I have to look at the equations a1, a2 up to an, that is equals to lambda times 2x1 up to twice xn. If I equate, I get a1 equals to twice lambda x1, a2 twice lambda x2 up to an equals to twice lambda xn. Once I have this, I know then that x1 equals to a1 by 2 lambda, x2 equal to a2 by 2 lambda up to xn equals to an by 2 lambda. Now since summation xi square equals to 1, that is x1, x2, xn lies on the sphere, I get that a1 square plus up to an square divided by 4 lambda square, that is equals to 1. Okay, I am just squaring and adding. So this gives me the value of lambda. I get that lambda is equals to plus minus okay. Now if I put these values of lambda, then I get actually two choice of critical points, correct? Because then the points actually I have are then a1 by 2 lambda, these are my critical points, a2 by 2 lambda up to an by 2 lambda. But lambda has got two values that we can see because I am getting a plus minus. So this is actually the collection of critical points. Okay, that means one of them will work as my local extremum, and I am searching here for the minimum value. Notice that the maximum value has also achieved because the function is a continuous function. So it will have a maximum and a minimum. So for one point I will have a maximum, for one point I will have a minimum. So how does one do that? Just I try to put the value of the points on the function and see what happens. So if I do that, so what is f of a1 by 2 lambda, a2 by 2 lambda, an by 2 lambda? Then I have a1 x1, that means a1 square plus up to an square divided by twice lambda. Okay, that means it is plus minus square root of now since maximum has to be bigger than the minimum, I will certainly choose the value minus, because one is a positive value, other is a negative value, so I will choose the negative value. Okay, that means if lambda equal to minus of square root of then a1 by 2 lambda up to an by 2 lambda produces minimum, and certainly the minimum value of the function that I can see from here, it is minus of, and minimum value is minus square root of So I think it's more or less clear now that what exactly one has to do. I will finish this with one more example which will provide an interesting proof of a very well-known inequality which all of us know. So let's move to the next example. So here the problem is find the maximum of the function f x1, x2 up to xn given by x1 square, x2 square up to xn square. such that x1 square plus x2 square plus xn square equal to c square. Look at the given function f, which is given by x1 square plus x1 square into x2 square up to xn square, and we want to maximize the function over the sphere x1 square plus x2 square plus xn square equal to c square. That means it's a sphere of radius c. So what I do is I proceed with the given one, that f of x1, x2, xn, that is x1 square, x2 square up to xn square, and the function g is given by x1 square plus x2 square up to xn square. So we have to start with again the method of Lagrange multipliers. So we start with grad f equals to lambda grad g. So what do we get if I calculate? So I get twice x1 into x2 square up to xn square, that is lambda times twice x1. That is my first equation. So what I am doing is I am differentiating the first equation, that is x1 square, x2 square, xn square with respect to x1. That gives me the left hand side. Lambda times then the partial derivative of g with respect to x1, that is twice x1 because rest are constant. I get lambda times twice x1. I am going to repeat this procedure with x2, x3 up to xn. So what I get then is twice x2 times x1 square, then x3 square up to xn square, and the right hand side then is lambda times twice x2, that is the partial derivative of g with respect to x2. I go on doing this. At the last stage I get 2 times xn into x1 square, x2 square up to xn minus 1 square, which is equals to lambda times twice xn. Okay. Now after this, what I do is I multiply all these equations. The first equation I multiply with x1, the second equation I multiply with x2, and the third last equation I multiply with xn. Once I do this, this implies that x1 square 2 lambda x1 square equals to 2 lambda x2 square up to 2 lambda xn square. Because if I multiply all these equations, the first equation I multiply with x1, what I get? I get 2 times x1 square, x2 square up to xn square equals to 2 lambda x1 square. Second equation I multiply with x2 on both sides, what I get is 2 x1 square, x2 square up to xn square, that is 2 lambda x2 square. I go on doing this. The last equation I multiply by xn on both sides, what I get is twice x1 square, x2 square up to xn square, that is equals to twice lambda xn square. Look at the left hand side. All the quantities are same. That means right hand side quantities should also be same. That means twice lambda x1 square is twice lambda x2 square up to twice lambda xn square, as I said. But since grad f and grad g both are non-zero, what I get is I can cancel the lambdas also. This implies then x1 square equal to x2 square up to xn square. But x1, x2, xn lie on the sphere of radius c. That then implies that n times x1 square is equal to c, n times x2 square is also equal to c, and so on. That means n times xn square is equal to c. So this then implies that xi equal to, these are equal to c squares, because that is the given equation. So I get xi equal to plus minus c by root n. Again I got two values as the extreme value, but whichever value I take, it doesn't really matter, because the function is given by x1 square, x2 square, xn square, because I am going to take squares of all the xi's. So even if I take minus, it is going to turn out to be plus. So the maximum value is the square product of all this. That means c square n times, that means c to the power 2n divided by n to the power n. So this is the answer to the problem that I wanted to maximize. I have maximized. Now some more comments in order. So I would put it as a remark. What I do here is, let x1 square, I call it a1, x2 square, call it a2, to xn square, let us say equal to an, and x1 square plus x2 square plus up to xn square, that is equal to c square for some c. Okay. Then I look at the quantity a1, a2 up to an whole to the power 1 by n. That means I am looking at x1 square, x2 square, xn square to the power 1 by n. Okay. Now I know the maximum value of x1 square, x2 square, xn square. As I have done in the previous case, it is c to the power 2n by n to the power n, but I am taking a power 1 by n, so it is lesser equal to c square by n. But then c square is x1 square plus x2 square plus xn square divided by n, but x1 square is a1 plus a2 plus an divided by n. What I finally landed up with is a familiar inequality which you all know, that is geometric mean is less than or equal to arithmetic mean. So using the method of Lagrange multipliers, one can actually prove that am is bigger than or equal to gm for n quantities. Now let us look back at the problem again. The given problem was, find the maximum of this function. The maximum is something which we were trying to look at. What happens if we ask about the minimum of this function? Well, a moment's thought would tell you that perhaps the minimum is 0. Why so? Because when I look at the sphere, look at the three-dimensional case, it's a sphere of radius c, then what is the coordinate of this point? The coordinate of this point, if this is x-axis, this is y-axis, this is z-axis, the coordinate of this point is c0, 0. What is the value of the function at this point? What is f of c0, 0? It is product of the squares of the component, but there is zeros appearing in the components. That means this is 0. And since the function is always non-negative because it is product of the squares, this is certainly the minimum value of the function. That means this point c0, 0 is a critical point of the function. Correct? So in the n-dimensional case also it is going to happen. whenever the sphere intersects the axis, then except 1, all the other coordinates are 0. That means if I look at the points of the form C, then rest at 0, or 0, C, rest at 0, and 0, 0, then C, rest at 0. Notice that all these points belong to the sphere S of radius C. Why these points, which are certainly minimum of the function, are not appearing as critical point in the method of Lagrange multiplier? That is a question. I look back at my calculations again. What are the points which served as the critical points here? That means the xi satisfies this. The point 0 does not appear here. The point C00, 0, that is what I mean. The intersection of the sphere with the axis. Those points are not appearing here as the points of extremum. Why is that happening? Well, the reason is very simple. The given function, notice, f of x1 up to xn is x1 square, x2 square, up to xn square. Okay? Now, what is grad f then? At any point x1, x2, xn, it can be easily calculated. It is twice x1 times x2 square up to xn square, then twice x2, x1 square, x3 square up to xn square, and it goes on like that. The last term here is twice xn into x1 square up to xn minus 1 square. I take a point C0, 0, that means a point on the axis. Okay? If this is the point, then I can see that grad f at C 0, 0, 0 up to 0, this is equal to 0. Because all the points x1, x2, xn appear in all the terms which I am writing here. x1 here does not appear as a square, but 2x1 appears. I look at the second term, x2 squared does not appear certainly, but twice x2 occurs. So all the terms are actually present, and one of the term and some of the terms are always 0 when I look at points like C0, 0, 0, 0, where it intersects. So the gradient of f at that point becomes 0. But look back at the method of Lagrange multiplier. I have always assumed that the points of local extremum, which I am going to find out, they satisfy two conditions, that grad f is not equal to 0 at that point, grad g is not equal to 0 at that point. If I look at grad of g, then at C0, 0, 0, 0, these points which I am looking at, grad g is non-zero. But grad f is certainly equal to 0 here, and that is why the method of Lagrange multiplier is failing here. So this is not the case that although the function is continuous, it does not have any minimum. It has a minimum, certainly. We could easily find out what is the minimum, but that point escapes the method of Lagrange multiplier simply because gradient of f was 0 at that point. So that finishes our discussion on the method of Lagrange multipliers. From the next lectures onward, we are going to deal with another important theme of calculus, that is integration. But this time we are going to do with functions of 2 or more than 2 variables, and we are going to talk about Riemann integration there.